is Caleb Bishop. I'm a junior at Keontae High School, and the focus, or my job on Moonriders, is understanding this device, the focus of this whole project, the electrodynamic dust shield, as you can see, is that we have here from Canon. So before I get into how it actually works, I'm going to talk just briefly about how the device came to be, some of its history. So in 1967, a NASA employee wrote a paper called Lunar Dust Degradation Effects and Removal / Prevention Concepts, and he talked about different ways we could deal with the problem of lunar dust being in the suits and on all the electronics and causing all these problems. So he just outlined the idea of using this type of system. He didn't create the actual device. In the 1970s, Professor Shinichi Masuda from the University of Tokyo began researching a very similar type of device. He was looking at pollution filters and mitigating smog particles. So it's two different types of particles that just need to be removed from where they are. He wasn't interested in space applications, and he later shifted focus. But in 2001, Dr. Carlos Calle, who founded the Electrostatics and Surface Physics Laboratory at Kennedy Space Center, won a NASA research agreement with the University of Arkansas at Little Rock, and they used Professor Shinichi Masuda's research and continued that for work with clearing dust off of solar panels on rovers that they had on Mars. After 4 years, that grant ended, and they shifted gears toward what they're working on now, which is the lunar dust. Okay, so the way that I like to think of the device as working is, as you can see, it's just there's a little circle in here. So how I like to think of it as working is you have a puddle of water with dust all over the top of it. If you throw a rock into the middle of it, it makes a ripple wave, and it pushes the dust outward from the center. But rather than water or a puddle, it uses electric fields. So this is a diagram of the device. It has 3 electrodes that are in this spiral configuration. So here's a graph of the voltage over time of an EDS running, and each color represents one of the 3 electrodes. So at any one time, one of the electrodes is positive and the other 2 are negative. And then it will shift to the other one being positive, green, and then red, and then back to blue. And it'll just cycle through one positive, next, going through all of these. So how these voltages actually create, there are 3 types of particles on the moon surface, or primary classes of particles that we need to be able to mitigate for this device to be working well. The first of these is any positive or negative charged particles. The second is polar particles. And lastly, there's uncharged non-particles, or neutral particles, because they have an equally distributed number of positive and negative surface charges. There's no net charge on the particle. So how the EDS deals with charged particles, the positive and negative electrodes create electric field going, as you can see here, from the positive towards the negative, and then they go in the opposite direction the other way. So a positive charge will experience a force on this side in this direction, and the negative will experience a force in the other direction. So it will kind of filter the positive and the negative charges onto either side of the electrode, and then as this shifts to the blue one being positive, it'll just the particles will hop with the electric field switching, and it will just hop out from the center off the rate of the EDS. So how the EDS deals with polar particles is, if there's an uncharged or no net charge polar particle on the EDS, or if a polar particle is exposed to a uniform electric field, the positive and negative poles of the particle will experience equal but opposite forces. So it will orient the particle with the electric field, but it won't actually move the particle. When a polar particle is exposed to a non-uniform electric field, such as that of the EDS, the positive and negative poles will experience unequal forces. So there'll be a net force, and then the particle will be removed. This is known as dielectrophoresis, and it's one of the primary forces that the EDS utilizes. Lastly, there's the uncharged nonpolar particles. So how it deals with these is that when the particle with the positive and negative, equally distributed positive and negative surface charges is exposed to the electric field, the positive and negative surface charges will migrate to the poles of the particle that are defined by the orientation of the electric field. And it will induce a dipole, an extrinsic dipole on the particle. and once this particle has that dipole, it can then experience dielectrophoresis, as I just discussed. Okay, so this is a equation that was provided to me in a paper from Kennedy Space Center. I don't fully understand it, but I can talk a little bit about the aspects that I do. There is the geometric properties of the particle, so a bigger particle would experience a larger force. And then there's the dielectric properties of the particle. So if a particle was more polarizable than the medium, it would fall into this category and it would experience a force towards denser electric fields. And if the particle was less polarizable than the medium, it would experience a force towards less dense electric fields. So on the moon, there's a very small atmosphere, so the particles are always more polarizable, so you're experiencing this force on this side. I guess I should go back to the equation. There's also the gradient of the electric field squared. So if that's the steepest shift in the electric field, which is why the EDS utilizes this square wave pattern rather than using a sinusoidal change from positive to negative voltages. It shifts sharply from positive straight to a negative voltage, and that increases the value of the gradient and results in a larger force. So I proposed writing a EDS simulation that will generate values of electric potential at points above the EDS, and I wrote this and sent it to Kennedy Space Center, and I then started creating it, or I have created most of it. So this is my thought process and my equation that I generated for figuring out these values. So I started with using polar coordinates r and theta, and I wrote an equation that would create just a spiral. So r equals s over 2 pi theta, where s is the spacing between the spirals. I then converted those into x and y coordinates so that I could use the point above the EDS that we're trying to find the potential at. And then with those values, I can find the value of r, which is the distance from the point on the EDS that I'm looking at, and the point above the EDS that I'm looking at, the potential. So initially I was thinking that I could use just an infinitely large number of point charges, just point charges going out in a spiral, and then I could sum those all up. But then I realized that that would be an infinitely large number of point charges, and then you'd have an infinite net potential. So I realized that there must be a linear charge density across an electrode. So the voltage from one of these little DLs would have to be equal to lambda times the distance, and where lambda is the linear charge density. So I ended up with this equation, which for at one point xyz, you can integrate around 2 pi n, the number of loops around the whole coil, and it would sum up and give you the whole voltage at one point. And then I just change the xyz and calculate it over and over and over and over again, and then I have a lattice of points where I have the voltages above the EDS. So this is the code that I wrote in Java to generate the data. So you can see there's 3 nested for loops, and then all the math is here in the middle. So it will calculate all of this, and then it'll shift one point over, it'll calculate it again, it'll shift, and it'll just calculate all of the different points, and then it exports directly into a text file, which are these numbers. So each one of these blocks represents a layer above the EDS, and then as you go to the right, you're going closer to the surface of the EDS. So the red values are smaller values, and the yellow values are larger, and then the green are even higher. So you can see it's kind of what you would expect. The values are higher as you get closer to the center. I then found this software called MATLAB and I haven't done a lot of work with it, but I began using it to try and visualize some more of my data. I just made a spiral. I'm only using one spiral at the moment. I have yet to incorporate the other 2 spirals. I plotted my points of electric potentials, and then I sliced through them, and there's different hotspots you can see where the values are larger.